All right, hello. Hope you're doing well. This will be the first video of chapter 3, and we're going to cover isotopes, and specifically how isotopes and their masses relate to the average mass of an element, which is found on the periodic table. So you may recall from lecture, there's this kind of formula that gives you the average mass of an element, and you take the mass of isotope 1 multiplied by the abundance of that, and you just basically continue for however many isotopes you have. So the mass of a particular isotope times its abundance, adding that up gives you the average mass. This is just a weighted average formula. So in this problem, we have two isotopes of copper, 63 and copper 65. And we don't know the abundance. We don't know what percent of each of them exists in nature. That's what we're going to try to figure out. So when we set up this formula, we know that the average mass is 63.546. So we can plug that in for our average mass. And then we know, and if we're not given a more specific mass, in this case, we're just going to use 63, because remember, this is the mass of a particular isotope in this upper left corner. And then if I don't know the abundance, let's just call it X, right? So then we have the second isotope, which is copper 65. The mass is 65. I don't know the abundance of that. Let's call it Y. So now we have two unknowns, which we need another equation to be able to solve this, since we only have one equation with these two unknowns right now. And the way you want to do this is remember that these two abundances, in percentage form at least, have to add up to what? Well, if there's only two, they have to add up to 100%. So in decimal form, which is how we want to represent it in this equation normally, this is divided by 100. So if you add up the decimals, they're going to add up to 1. So in decimal form, X plus Y will always add up to 1. Okay, so that's our trick. So then we can say either, X is 1 minus Y, or Y is 1 minus X. Substituting that in here, we now have a algebraic equation with only one unknown, X, which we can solve for, or if you solved for Y or X in terms of Y, you would only have one variable, which is Y. Doesn't matter which way you do it, you get the same answer in the end. You can try it both ways. But anyways, basically solving for X, I'll leave out the particular algebra steps. And we get 0.727. Okay, so now to answer the question, that represented the abundance of copper 63. So our copper 63, but this is in decimal form, so we want to multiply it by 100. So we're going to have about 73% or 72.7% of copper 63. Right? And then copper 65 is just going to be 1 minus that, which is 0.273, which will be 27.3%. And you can check that these add up to 100. Okay, so one thing with a kind of a conceptual way of looking at this problem, especially with multiple choice type questions, if you're running out of time and you have to guess, one way to make a really smart guess would be look at the average mass. The average mass is 63.5 basically. So imagine that copper 63 is a red isotope and copper 65 is blue. If you had an equal mixture, you'd have this kind of purple right in between. But if that purple had more of a reddish tint, like a reddish kind of purple, you could say, oh, there's got to be more of the red one in there, or vice versa, the blue one. So this mass is closer to 63, this average mass. So that's why there's more of the copper 63 and then the copper 65. So just from a weighted average concept, you can look at this average mass and then determine which one there should be more of in a mixture of the two. Okay, so just for practice, another variation on this problem. We have a problem involving potassium, which has 3 isotopes. So this is 50% more fun. It's just math. And if we kind of maybe summarize our data, so we have potassium 39, 40, and 41. And then we have these masses that are given. So in this case, we're going to use these more specific masses if they're given. And indeed, if you measure the mass of atoms and isotopes with particularly specific instruments, you get these sensitive ways to measure and gets very, very accurate numbers, which don't actually turn out to be whole numbers for complicated reasons that we can get into in Chem 1C. Okay, so the abundance, let's say we'll just keep it in percentage form. We have 39 it's mostly potassium 39. And then we have, that's potassium 41, 6.73%. So again, we're gonna have an unknown percentage here. So we have the two unknowns. Same kind of formula that we want to use. And first, let's think about what we can find with this here. So we know that these have to add up to 100%. So maybe a first, step in our problem-solving strategy would be, let's find the percent of potassium 40. So this percent would be 100 minus the other two summed up, which is going to be about 1%. Okay, so we have that number. Very small amount of that one. Okay, so now we can use our formula, and if we look on the table, then we can get the average mass of potassium, which is 39.10. This is the average mass. Right, so remember from the table, when you look at a particular element, so you'll see like potassium, and then it'll have underneath it the average mass, right? So that's what we're looking for. Okay, so this is going to equal, again, just setting up our formula. We have mass of isotope 1. Here we're going to put it into its decimal form, 0.9326. And then we have 39.964. 0.01 divided by 100 is going to be 0.0001. Right, again, so this is the percentage divided by 100. And then we'll have our last one, which will be X. That will be our mass of potassium 41. And we have 0.0673 for the abundance, again, percentage divided by 100. Okay, so solve for X. And no surprise here, it should be close to 41 because that's what we're calling the mass, or that's the mass from the symbol. So specifically 40.95. Okay, hope that helps. Make sure you know how to use this formula and practice these variations on these types of problems to get good at it.